Okay, so we talked about facilitation. Now let's go over another part of modulation that is affecting our synaptic efficacy. This one is the opposite of facilitation. It is depression. So they can induce depression of synaptic transmission, which is reducing the overall efficacy of neurotransmitter release. And so it just does the opposite. It makes that postsynaptic neuron less sensitive to any presynaptic signal coming to it. And in this example, we're going to look at adenosine and how it can induce depression of synaptic transmission. So let's take a look. All right, so this looks familiar here. Same setup as before with serotonin. But this time we're not really concerned with directly neurotransmitters coming out, but we will see that this will be, in this example, we'll be talking a little bit about dopamine. So this is the monoamine, the neurotransmitter dopamine. Finally, talking about the neurotransmitter that that these lectures are centered around. And so in this example here, we have what we call the A2A receptor. And in fact, I've sort of messed things up here because I have our dopamine attached. That was not quite my intention here, but let's do this. I'm going to draw another one. Let's see, 1, 2, 3, 4, 5, 6, 7. Yes, blue. I would like blue. Okay, so we have, these aren't meant to be the exact same receptors, but they're both metabotropic receptors, G-coupled protein receptors. And this one, which I labeled A2A before, was incorrect. This is actually a D2, dopamine 2 receptor, and this is our A2A. So what is an A2A receptor? Well, this is our adenosine 2A receptor. Adenosine, and it's the 2A. There are a number of different adenosines. And so what is adenosine? Well, it is a component of ATP, if you remember. So ATP, which is a way our cells store energy, transfer energy around. And so let me draw ATP here. And I think this may seem like extra information than you need, but I think this will be useful when we talk about a practical application of this process that we've all experienced, but have never thought about it in this sort of detail before. I'm going to run out of room, I'm afraid. Don't want to forget my hydrogen there. Okay, so I'm drawing the structure of ATP here, adenosine triphosphate. I do my best not to. And the reason why I'm drawing it here is because I'm going to draw a different, I'm going to have to poke into our presynaptic neuron here. I'm going to show another molecule that's very similar to ATP, right? And so this right here we have our our triphosphate group here, and our adenosine is this section here of the molecule. And so this A2A receptor binds to adenosine. And so when would we see adenosine? Well, we would see adenosine when we've cleaved all of the phosphates off of this group. We've maximized its energy giving its energy transferring ability, and it's just adenosine, and it's in its sort of lowest state without the phosphate groups, and it's sort of useless in terms of being able to give energy to phosphorylate other, or to contribute a phosphate group through phosphorylation to other molecules, other proteins. Right, so this is in its lowest state, and adenosine builds up when we've used lots of energy. And so let me draw let's pick some purple here, and we'll make purple our adenosine. All right, so adenosine is gonna bind there. Okay, so what this does, well, specifically to talk about depression, and this isn't depression in the psychological condition, but this is depression, the neuromodulation. Two different things here, two different scales. This is just on the scale of receptors. We're not talking about the clinical depression. And so what this does through our G protein here, it signals through secondary messengers. It signals to our D2 receptor. Specifically, it reduces its affinity for dopamine. Reduces the affinity. And so what that means is that dopamine is more likely to not bind to it. All right, so as dopamine is floating around, the D2 receptor just isn't going to hold on to it. That the probability that dopamine will bind to it, given a certain concentration of dopamine, is reduced. Right, so its affinity is less. And so what are the effects of this? The reduced affinity for dopamine at the D2 response. Well, it decreases arousal and decreases behavioral activation. And what I mean by that are things like motivation and movement, physical movement. And so that's depression, pretty simple. But I also want to go just a little bit further here to take advantage and talk about another example involving the A2A receptor here. This also will, in neurons that release GABA, right, or gamma aminobutyric acid, which is our main inhibitory neurotransmitter. What it does is it promotes its release. So GABA release is promoted through the signaling of the A2A receptor. So we can see that it increases or decreases the affinity for dopamine in the D2 receptor. It increases GABA release, which is inhibitory. So it's going to quiet, it's going to induce inhibitory postsynaptic potentials on any other neurons that this postsynaptic neuron will synapse onto. And I want to introduce yet a third receptor here, and we'll put it right over here. And this is another metabotropic receptor. This is the A1 receptor. Adenosine 1 receptor, right? So this is going to bind adenosine. And what this does, I'm not going to talk about the molecular cell signaling, but I'm going to, through secondary signaling, it manifests itself as it slows metabolic activity. It also reduces synaptic vesicles and excitosis. So I'm just going to say excitosis. And exocytosis. There you go. Thank you for bearing with me. And I'm going to talk about just one thing in particular, this reduced exocytosis, this reduced vesicular release will result in the depression of heart rate. Specifically. And so this adenosine signaling, so when our body has used up a lot of ATP, adenosine is floating around and it's binding to A2A and A1, which results in decreased arousal, increase of inhibitory transmitter release, slows metabolic activity, and decreases our heart rate through reduced exocytosis of neurotransmitter. This is getting tired. This is part of getting exhausted, getting tired, which is part of the, which facilitates sleeping. Right? And so we've all experienced this. Certainly at night before you fall asleep, or perhaps on a Monday morning when you've gotten up earlier than you should have, and you just feel really tired. You've got a lot of adenosine floating around, free adenosine. It's making you groggy. And so what's the thing that a lot of us do? Well, we drink something with caffeine in it. Something that, right? What is it? The most popular drink in the world is water. The second most popular drink in the world is tea. And the third most popular drink in the world is coffee. So in the top 3 drinks in the world, 2 of them we drink probably because it has caffeine, arguably coffee and tea, would not be number 2 and number 3 if it did not have this a little molecule here called caffeine. And let me draw it out for you. Okay. And the reason why I'm drawing this one is so that you can see how similar it is to adenosine. Let me see, let me make sure I get my 1, 2, 3, 6, yes. Oxygen here, a methyl group there, oxygen there, another methyl here. Yes, I believe that's it. I think we have all of our 4, 3, yep. No double bonds there. And so this is caffeine, and so it looks quite familiar, right? This structure here, quite familiar to part of our adenosine up here. And so it's no surprise that looks like we need another color. Let's make caffeine, how about orange? So caffeine here. What does it do? Well, when it's in our system, crosses the blood-brain barrier, and it can bind to our adenosine receptors. So I'm going to actually put them over the adenosine here because it is an agonist, competitive agonist. And caffeine binds to A2A and A1. It does not let adenosine bind. So adenosine will try to bind, but it will be rejected. And though caffeine binds to it, it does not activate, right? So all of these downstream effects that we get here, we don't reduce the affinity for D2, and so we don't get this decrease of arousal and behavioral activity. We do not get a promoted release of GABA. We do not slow metabolic activity. We do not reduce exocytosis, which results in depression of heart rate. In fact, you can get the opposite. Too much caffeine can increase heart rate. So this is our immediate answer to too much adenosine, getting too tired. Just block it for a little while, that's fine. But what happens when, and likely most of us have experienced this as well, what happens when that caffeine starts to wear off? Well, while caffeine is blocking A2A and A1, in the background, your body's still going through metabolic processes. It's taking phosphate groups off of ATP and ADP and AMP to go about its business. And that results in a buildup of adenosine that continues to be blocked by calcium. But eventually, you metabolize all that calcium. It leaves your system. It's no longer around. And all of a sudden, you've got a huge flood of adenosine that just nonstop interacts with its receptors. And you have a big flood of, once again, all of these activities. Right? I'm not going to be able to, I'm erasing the effects here, but I think you get the idea. This turns on the floodgates again for all of these systems, all of these pathways that once again decreases arousal and promotes GABA. It's stronger than it ever did before because you built up all this adenosine. And this is the crash. This is the caffeine crash as a result of this. Okay, so thanks for humoring me on that little tangent about caffeine. Well, let's move on to the next example. Okay, just one little extra note here is I want to make sure that I write this out in specific. I think I might have said agonist before, and that was incorrect, right? Caffeine is not an agonist. An agonist is a compound that induces the same sort of effects on the receptor. Caffeine does the opposite, right? It renders the receptor inactive, and so that makes it a antagonist. An agonist would be something that kind of does the same thing that adenosine does, but it's not. And caffeine binds to the same site as adenosine, and so we call this a competitive antagonist. Okay, so caffeine is a competitive antagonist for adenosine at sites for the A2A receptor and A1 receptor. Okay, let's move on to our next example. Okay, so the next neuromodulator, or the next neuromodulatory effect that I want to talk about is desensitization. All right, so neuromodulators can lead to the desensitization of receptors, making the postsynaptic neurons less responsive to subsequent neurotransmitter binding. The example that we're going to use here is prolonged exposure to opioids, such as morphine. This can lead to the desensitization of our opioid receptors. And we have endogenous opioids because we have these opioid receptors that things like morphine and fentanyl and heroin bind to. It's because our own body produces its own opioids, such as endorphins that bind to these. So let's take a look. Okay, there's no need here for our presynaptic neuron here because we're talking about opioids. We're talking about something that we're taking exogenously. Okay, so and in this case, right, I said that this was morphine, but this will be similar for other exogenous opioids like fentanyl, heroin, so forth, OxyContin. And so when a morphine binds to this receptor here, which is our, I'm going to put it over here so that we can save room for our intracellular pathways. This is our, what we would call opioid receptor mu, the Greek letter mu, often just known as the mu receptor. All right, so this is a specific opioid receptor, and it binds to this. And this obviously facilitates and gives rise to both the euphoric experience that you get with opioids, but also the addictive property of it. But let's talk about desensitization. So when you take opioids over extended periods of time, users will experience a desensitization. So they require more and more of the drug as they build a tolerance for it, or more specifically, more appropriately, a desensitization to it. And that's because of the signaling that happens by prolonged binding. So binding to this metabotropic receptor sends off a feedback on the receptor itself. And so through this secondary messenger system, we phosphorylate our own receptor, our mu receptor. And so this, I'll write it out here, phosphorylation of the mu receptor results in a decrease affinity for this ligand itself. Right? And so that, in a sense, is quite simple here, even though we're not looking at all the biochemistry here for desensitization. It also has a number of other effects as well that contribute to a loss of the effects of the drug here. We experience through the mu receptor and other secondary messaging systems, we experience a closing of our calcium channels. These are voltage gated channels, so we'll close these calcium channels with chronic use, and in turn we'll open other channels. We'll open potassium channels as well. So potassium can leave, and our calcium will not be able to get through. So it makes it harder for this neuron that has these mu receptors to fire an action potential. It keeps them quiet, right? And this is an important process in one of the efficacious uses of opioids, right, which is pain relief. And so in this real-time metabotropic effects, it sort of quiets these neurons. And so these would be neurons that the target for this would be neurons that are associated with nociception, pain perception. And so if you could turn off those neurons that are sending pain signals to the brain, you won't feel that pain. That's great. But as we see over time, it takes more and more of these opioids to induce the same response, because as our receptor becomes more and more desensitized to it, that means that we get a decrease affinity for the morphine. So the same concentration of morphine will result in a lower probability of it binding to the receptor. And so this desensitization is a explanation for the phenomena of being on opioids and having their effects wear off over time and needing greater concentrations of it. Okay, let's take a look at the next example. Okay, next I want to talk about sensitization. Just the opposite of the neuromodulation that we know as desensitization. So neuromodulators can induce this, making the postsynaptic neurons more responsive to subsequent stimulation of inputs. And the example that I want to go over is the sensitization of neurons in the pain pathway by a substance that we call prostaglandins. And this can contribute to that, to pain perception. Okay, here we are yet once again with our metabotropic, our G-coupled, or G-protein coupled receptor. And I'm going to write up here so we don't forget that we're talking about sensitization. And first, let me introduce this compound that I mentioned before, prostaglandins. And so prostaglandins are lipid compounds. They're derived from the membrane. And we can think of these as a hormone-like. Or a signaling molecule. Now, we're not going to call them hormones because technically they aren't, because they don't get delivered in circulation. They're not dropped into the bloodstream and travel around the body to distant target tissues, but rather locally. They aren't involved in the traveling across the body in the bloodstream, but rather they're local signals. And prostaglandins, they bind to this receptor right here, which is it's known as the EP receptor. And EP just stands for, not that you need to commit this to memory, but it's the E-type prostanoid receptor. And prostanoid is just prostanoids are a larger, or prostaglandins are a subtype of prostanoids. Prostanoids, which include prostaglandins, are lipid compounds that are derived from polyunsaturated fatty acids. Prostaglandins are a specific type of these, and they are derived from the cell membrane itself. And so when a prostaglandin binds, and we'll make these, since I wrote sensitization in purple, and I'll sort of underline it here in purple, prostaglandins will be purple here. And they're produced, I should write this here, in this context of this context, they're produced in great abundance with tissue damaged. Right, which is something that typically, as we would subjectively describe it, as painful, something that hurts, tissue damage. And so it's produced in it, and it binds to these EP receptors in our neurons, in our nociception pathways. And so what does it do? Well, it, secondary messengers again, signal cascade. It will give us calcium. It will liberate calcium, which will signal something that we call protein kinase C. And we talked about kinases before in passing, PKC. Protein kinases are enzymes that facilitate the transfer of phosphate groups from ATP or ADP to a protein. Right? So it is an enzyme that's necessary for phosphorylation. And so what does it facilitate the phosphorylation of? Well, in this example here, I should do a different color. What it's going to do is come up here and, ADP plus phosphate group. It's going to phosphorylate voltage-gated sodium channels. So voltage-gated sodium channels. And in this example, in this where it specifically phosphorylates this one, what effect does it have on our channel? Well, it lowers the membrane potential activation threshold. Lower the membrane potential activation threshold. And so what does that mean? We've seen an example of this before, right, when we talked about excitability of our neurons. And so it will make these voltage-gated channels more sensitive to any change in the membrane potential. So it gives them a hair trigger, so to speak. So making these more sensitive to initiating an action potential once they've received a excitatory input, such as glutamine, for example. So we still need, right, glutamine perhaps to get things going here. And this will make the effects of glutamine more, will potentiate the effects of glutamine sort of indirectly by reducing the depolarizing threshold that you need to open up these voltage-gated sodium channels. And I'll also talk about another channel that they sensitize. This is something that we haven't mentioned before in class. And this is something that's called transient receptor potential channels. Let's see, potential. There we go. And a specific, in this context of tissue damage, and we're talking about the nociception pathway here, the specific type of TRP that we're talking about is something that's called a vanilloid receptor. And this is a receptor it's a channel that responds to heat. So when it experiences an increase in heat, the channel opens, and it facilitates an excitatory signal by letting positive ions, sodium ions, to flow in. Actually, don't quote me on that. I'm not sure if the vanilloid receptors are sodium or calcium. But they facilitate an excitatory response. And just sort of an interesting little side note, the reason why I bring this up here, right? And so in this context, our EP receptors will sensitize. So it increases sensitivity of our vanilloid receptors to heat. And so it doesn't take as much heat for them to open up. But this vanilloid receptor is also sensitive to a compound called capsaicin. capsaicin. Let me check that for spelling. Yeah, okay, capsaicin. And this is the active compound that we see in chili peppers that gives them the hot nature. And so capsaicin binds to vilanoid receptors and activates them in the same way that heat does. And so it's no wonder, no surprise that both heat and capsaicin will result in the same subjective experience of heat, right? The chili peppers, when you eat them, feel hot, and in fact, next time you eat something spicy, it will increase your sensitivity to hot things. So something that previously was sort of warm will feel hot in your mouth when you already have capsaicin, because it's already activating this pathway and sending those signals to the brain. Okay, so a couple examples here of sensitization.